So before we go to the next example, I want to give you a one important concept related to Stokes theorem. Now, Stokes theorem basically tells us to evaluate a line integral over a closed curve using a flux integral. Now, this flux integral is calculated on this surface S. So let's say we have a surface. Let's say we have a surface S1 with the boundary C. Let's say this is the boundary of the surface S1. It's the boundary of surface S1. Now we can have another surface with the same boundary C, maybe something like this. This is your surface S2. So according to Stokes theorem, this line integral, let's say we have a vector field F, then the line integral over the closed curve C equals to flux integral over the surface S1 so here we have S1, but if you think about this blue surface, then it has the same boundary as the surface S1, so this line integral must be equal to the flux integral over the surface S2. Okay. Now, so when we use Stokes theorem, if we have two surfaces that share the same boundary, you can consider the simplest surface out of those two. And now remember here, the only difference is the normal vector field. If you consider surface S2, you have a, let's say, normal vector field N2, but if you consider surface S1, then you have the normal vector field N1. So that's the only difference. Okay, let me show you the application of this knot through an example. Okay, let's say we want to calculate the value of this line integral over the closed curve C, where C is the cone, C equals to square root of x squared plus y squared, intersects the plane C equals 1, oriented counterclockwise viewed from above, and our vector field F equals to this. The first component is sin x minus y cubed over 3. The second component is cosine y plus x cubed over 3 and xyz. Okay, now, so here we have two options to calculate this flux integral. Okay, so if we do this, let's say line integral over the closed curve C, this equals to a flux integral curl F dot n ds over the surface S. Now here we have two options. If you think about this cone and this plane C equals to 1, now the curve of intersection is this C. Now for C you can consider two surfaces. One surface is the surface of the cone, which is this one, in that case you should consider the normal vector field for the surface c equals to square root of x squared plus y squared. So this will be your normal vector field. And the second option is you could consider this plane c equals to 1. So c equals to 1, and then your normal vector field should be something like this. You have a very simple normal vector field. Again, as you can see, this boundary shares two surfaces. One surface corresponds to the cone and the second surface corresponds to this plane c equals to 1. Now as you can see, if you consider this normal vector field, it will have three components. If you go over the example, the fourth example that we did in chapter 13.5, we calculated the normal vector field for a cone. But if you consider the plane c equals 1, its normal vector field points in the positive c direction, and in fact this normal vector field equals to x component should be 0, y component should be 0, and the c component should be 1, because that points in the positive c direction. So at every point on this surface, if you consider a normal vector, outward pointing normal vector, those normal vectors point in the positive c direction, and that the equation of the normal vector should be 0, 0, 1. So let's use option 2 to calculate this this line integral. So here I am going to consider option 2, and first we need to calculate the curl of f, and I did it over here. Now in this particular case, your normal vector field should be, not the normal vector field, sorry, the curl of f should be xc comma minus yc comma 3x squared plus 3y squared. Okay, so then the line integral over the closed curve c of f dot ds little s, this equals to curl of f dot n ds over the surface S. Curl of f equals to xc comma minus yc comma 3x squared plus 3y squared dot, your normal vector is 0 comma 0 comma 1, and then ds, in this particular case ds equals to dA, and here we should have the domain D, and your domain D is the projection of this onto the xy plane, and this is, so at this point we have c equals to 1. So if you consider the equation of the cone and the equation of the plane and set them equal to each other, you will get the equation of this curve, which is square root of x squared plus y squared equals to 1. This is a circle with radius 1. And that's your domain D. That's your domain D. Now here I said ds equals to dA because the equation of the surface is SA equals to 1. And so ds equals to square root of 1 plus f sub x squared plus f sub y squared dA. Now here we have a, this is your f is 1, it's just a constant. So these two partial derivatives equals to 0, and you will get square root of 1, which is 1 equals to dA. Therefore ds equals to dA. Okay, now if you simplify this integrand, you will get just 3x squared plus 3y squared dA over the domain D. Now as I mentioned earlier, your domain D is a circle with radius 1. Therefore to evaluate this double integral, let's use polar coordinates. If you factor out 3, then you will get x squared plus y squared, and in polar coordinates x squared plus y squared is r squared, and dA is r dr d theta. R goes from 0 to 1, theta goes from 0 to 2 pi. We can pull out 3 from the integral signs. Dr d theta. Now let's integrate r cubed. If you integrate r cubed, you will get r to the power 4 over 4. Apply the upper limit. So you will get 1/4 minus the lower limit. The theta. So 1/4 is a constant. Now we have the integral of 1 d theta. This equals to 3/4 times theta. Lower limit is 0, upper limit is 2 pi. Apply the upper limit minus the lower limit. So 2 pi minus 0. Basically you can simplify this. 3 pi over 2. 3 pi over 2, and this is the value of the line integral f dot ds over the closed curve C. And to evaluate this line integral, we use the Stokes theorem. And when we use the Stokes theorem, we had two options to select the surface that has the boundary of C, and we selected the surface with the simplest normal vector. With this, I finished chapter 13.6, and next we are going to so next Thursday we are going to do chapter 13.7.